So the notation for today is as before. P is a prime number. G is a finite group. But today I'm going to, so in the first lecture I mentioned that if you want to do P blocks of G, there's a bijection whether you consider the group algebra over O or over little k. And so for convenience sake, for this lecture, when I say, I'm going to identify blocks over O with blocks over k, and when I want to distinguish between, really emphasize the difference between them, I'll say so. Okay, and so I will just say B is a P block of G. Okay, just like that. And also, so okay, now I want to recall some important things that are associated to this to a given block. Okay, so already, I mean, we've seen this in several lecture series. So what is very interesting is, I'm changing notation a little bit again from my first lecture. So this is ir capital KB, which was what I called ir k tensored over O of B. This one is just a little bit less clunky, so I'm going to use this. And what is this? This is the irreducible simple modules of this semi-simple algebra, or now for today, let's just think of this as the subset of the ordinary irreducible characters of G, which belong to B, so or associated to B. Okay, and we also had the modular characters, and this is what I would have called in my first lecture this set, and this is the subset of irreducible Brouwer characters. In B. So these are two very fundamental things associated to any block. Okay, and in yesterday's lecture, we started looking at the local sort of P local information in terms of P subgroups of G. And so we defined, for any P block of G, we defined a subgroup or a class of subgroup, P, and another block, B star. So I just quickly remind you, so this is a defect group. Of B, and for unique up to conjugacy in G, and once you fixed a defect group, this was the block. So this is the block of the normalizer, so P block of the normalizer in G of P, having P as defect group with P as defect group. In Brouwer correspondence with B. And let me just remind you what the relationship between B and B star, even though it's not really going to show up again, but the relationship was Brouwer P of B is the same as Brouwer P of B star. Okay, where Brouwer P was the map. Now we're just going to think of it as the map from the fixed points of P on acting by conjugation on Kg to the group algebra of the centralizer in G of P, and this was just the truncation map. I don't write it down again. This is just to recall sort of the context. It's a Brouwer homomorphism. Okay, so so this is sort of the pair P and B star. It's really, I mean, the way I think of it is it's the top layer of the local structure of B. Okay, so I've been considering the Brouwer homomorphism now for with respect to this P subgroup P, but you can also, of course, look at it for other P subgroups of G, right? In particular for the subgroups of P itself. Okay, and when you allow yourself the entire post set of P groups, you can enrich this top layer. You get data at every layer, and you can package that together in a quite formal way as a fusion system. I'm not going to talk about those. And the whole data of the fusion system is the entire local structure of P. Okay. But I thought today I won't go into that. I won't develop that theme further because I really want to give a flavor of different things that are going on in the subject. So I'll just use this top layer for today. Okay, so what I want to discuss first is, so we've been setting up all this theory. There's all these, beautiful definitions, and conjectures, of course. And so I wanted to give an idea of how the things actually work, right? Give some result which shows block theory in action. Yeah. So, for example, if you have two finite groups G, G prime, a block B of G, block of G prime, how on earth do you start deciding, is there any nice equivalence between them? Okay, so I'm going to give you just one example of a criterion that you can use, that has been used in many cases to decide that two blocks that you're looking at are indeed Morita equivalent. Okay. Okay, so let me just give this is like just a sample thing to give an idea. And it uses everything sort of that we have up here, okay? And the result is going to be a Morita equivalence. The conclusion is going to be then this block is Morita equivalent to this other block. Okay, and it's going to use ordinary character theory. So it's local global character theoretic criterion for a Morita equivalence. Actually, this does not really deserve such a grand title, but I'm just saying it because I want to say that everything works together. Okay, so you want to use all aspects of this picture when you're doing block theory. Okay, so what is the setup here? Well, I want to show that two blocks are Morita equivalent. And I think, like I said yesterday, so if you want to show an equivalence of module categories or derived module categories, you've got to have some functors between those categories that you can understand. And a classical, most used functor is induction and restriction. Okay, so my setup is going to be that I have a subgroup H of G, and I'm going to just look at induction and restriction. Okay, and I want to be able to calculate things. So in some sense, if you have a group, say finite simple group or any other group about which you have some information, then you might have its character table, you might have some information about its subgroups, and you might be able to, figure out or have a computer figure out for you how irreducible characters of H induce to irreducible to characters of G, and so on. So, okay, and now this is what we're going to use, and now let C be a P block of H. Okay, so I'm going to define a couple of numbers here. So for chi belonging to, this is all just ordinary characters, chi belonging to an irreducible character, ordinary character of H in the block C, I'm going to define the integer I from, I'm going to call it from C to B of chi, okay, to be just the number of irreducible constituents of the induced character from H to G of chi, okay, which appear in the block B that I'm interested in. So I want to go from C to B. I start from a character of C. I induce up to G, and then I throw away everything that's not in the target block, so in B. So induced character lying in B. And this is with multiplicities, okay? So with multiplicities. Okay, so if you understand you're in a situation of a pair of groups where you can do this, then you can calculate this number. And then I'm going to let IC to be the max over all characters of C. Okay, so we have this number here. Okay, so now what's the criterion? So I'm going to suppose that H and G have a common defect. B and C have a common defect group. So I suppose that P is a subgroup of H, and it's also a defect group of C. Okay, and I'm also going to suppose that B and C have the same number of ordinary characters. Okay, because there's no harm in assuming this, because if they don't have the same number of ordinary characters, they are not going to be Morita equivalent. Okay, so let me just draw somewhere. I want to just draw a little picture. It's my board problem again. Sorry. Okay, I'll just draw it here, and then we'll see what happens. Okay, so H is contained in G. And I have my block here, C of H, and my block B of G. Okay. Okay, let me just finish this picture. And now I also want to bring in some information, local information. So I have a normalizer in G of P, and I have the normalizer in H of P. Okay, so normalizer in H of P is a subgroup of the normalizer in G of P. And I have my Brouwer correspondence, C star and B star. Okay, and I'm going to now make a couple of local assumptions. Okay, I'm going to make an assumption on the structure of the normalizer of P. Okay, because this is not strictly necessary. I mean, I can weaken it, but just to make things look a bit smooth for this talk, these are the assumptions. So suppose that. So this is going to look a bit artificial, but it actually occurs quite often, this situation. So suppose that the normalizer in G of P can be written as a direct product, okay, of a group G0 with a group N, such that P is actually sitting inside N, and N is sitting inside H. Okay, and if I look at the centralizer in N of P, I don't get anything much. I just get the least possible. I get Z of P. Okay, so suppose this is this is quite strong condition on what the normalizer has to look like. Okay, and I'm also going to make one other assumption. also a local assumption, and also not always necessary, but makes things easier to state. And the second assumption is that Brouwer P of B is a single block of KCGP, and Brouwer P of C, same thing, is a single block of KCH of P. So remember, the Brouwer homomorphism goes to the centralizer in G of P, and it in general picks out a product of blocks. So I want to make this simplifying assumption that it's not picking out a product, it's just picking out one block. Okay? This is not always necessary. Okay, so there are these kind of annoying, restrictions. They are real restrictions. So this doesn't always work. Anyway, so what's the criterion now? So you count a global multiplicity and you count a local multiplicity. So if you have that 0 is less than IC to the B, okay, and that happens to be less than or equal to the count that you do at the local level. So you do the same thing. Now you're looking at characters of the normalizer in H of P to the normalizer in G of P. And if you get this, okay, then that's it. B and C are Morita equivalent. Okay, and so, okay, you could, how often does this happen? That's another question. I will say a little bit about that. But it's a situation where you have to do some calculation, so you have to do some work, okay? But the calculation is at the level of ordinary characters and just induction. Or we could do restriction if you prefer, okay? And then so supposing your computer can calculate all these things, no problem. And then you just compare these two numbers, and it looks pretty, it looks very innocuous condition, but it is a fact that then these guys will be Morita equivalent. Okay, and then, so again, well, is this ever used? And it turns out that, it has had quite a few uses, because actually this situation occurs a lot, okay? So in finite groups of Lie type. So if you want to compare, for example, a block of GLN with a block of a GLM where M is smaller, or for symmetric groups, whatever, there are many, many pairs which satisfy this condition. Okay, and so it's been a useful criterion. Okay, I should confess. So this appears in a paper of myself and Gerhard, but it's a strange criterion because all the applications of it were found before we formulated it. Right. So since I discovered that it has this really smooth way of saying it, I've not used it again. But it had been pre-used loads and loads of times. Okay, and in fact, the first time where actually this argument was used, not in this way, but was in a paper of Joanna Scopes in the early 90s, where she showed that Donovan's conjecture holds for blocks of the symmetric groups. Okay, and so this is sometimes, this kind of theorem is sometimes called Scopes reduction. Okay, it's been quite useful for settling many cases of Donovan's conjecture and so on. Okay, I should say, of course, here I started with induction and restriction. I should have said that earlier. You can replace induction and restriction by any piece of it that you understand. Okay, so you don't have to, so Harishchandra induction, for example, is how it's used a lot. There's nothing, you just need that it's a summand of induction. So instead of doing induction here, you do Harishchandra induction. It's fine. Okay. It doesn't change the criteria. Okay. Okay, very good. Actually, maybe I can say second, I can give just one example where you can easily see that this local criterion can be satisfied. Okay, so for example, in the symmetric groups, if you take, so you look at some multiple of some integer w, okay, and it sits inside some symmetric group Sm in the natural way, which in its sits inside Sn, and you let P be a seal of P subgroup of SPW, then this, if I make this guy equal to G, this guy equal to H, and this guy equal to N, you will see immediately that there is this direct product decomposition, and in the piece on which the the P actually sits, it's self-centralizing. Okay, because if you have a seal of P subgroup of acting transitively, then there's okay. So it happens all the time, and now you can probably see how you would have this thing replicated. And of course, to make this relevant is that all defect groups that appear in blocks of symmetric groups are precisely seal of P subgroups of subgroups of this form. So you can see where it goes. Okay, so that was just all I wanted to say about that. And like I said, I think I've already squeezed every possible application out of this criterion, but if you ever find one, or you happen to be doing something and some weird-looking inequality comes out, then maybe there'll be another Morita equivalence there. Okay, so now I want to switch a little bit again and talk about abelian defect. Okay, so I want to just spend a little bit of time on the condition abelian defect groups. Okay, because it comes up a lot. So why do we care so much about abelian defect? I mean, most P groups are not abelian. So why does this attract so much attention? Well, you already saw one thing, which I will mention again, Brouwer's conjecture. But I also want to say a few more things here. So, okay, first of all, what is one feature of having abelian defect? A special feature, which I'm not going to explain rigorously, but I just want to bring it back to something I was saying at the beginning when I said that this P and this B star is in general just the top level of the local structure of the block P. Okay? What makes abelian defect so nice, so if P is abelian, what's a very nice property then is that the top level is all you need in some sense. P and B star is all you need. And actually this is nothing really, it's a very classical fact. This is Burnside's theorem, which says that fusion in a finite group with abelian seal of subgroups is controlled by the normalizer. Okay, so that's just a fancier way of saying that whole thing. So that is the reason why, one reason why we like this condition so much. Then maybe Gabriel already mentioned this case when talking about the Alprin-Waite conjecture, but we saw the Alprin-Waite conjecture in Gabriel's talk yesterday. If P is abelian, then this becomes much easier to state, okay? And all it's saying is that the irreducible modular, the number of irreducible modular characters of B is equal to the number of irreducible Brouwer characters of B star. Okay. Okay, and then, right, let me again mention the abelian defect group conjecture. Which says that if P is abelian, then derived B, let me just write it a bit loosely, B and C are derived equivalent. Okay, now I'm just going to B and star. Yeah. What did I say? Are equivalent. Derived equivalent. Okay, so I'm just now going to talk a little bit around the, just one comment I want to make about the abelian defect group conjecture, and just show you, okay, it's beautiful anyway, because it's just predicting this, very nice correspondence, but there's another feature to it, okay, which is, why do we care so much about this, in one way, is that the structure of B star is totally understood. Okay, so B star has a very easy to write down structure. So I'm going to write it down now. And then thank you. And this is a result of Kuhl's hammer. Okay, so which says, and actually it's more general, it doesn't need the abelian P condition. So this is theorem Kuhl's hammer, which says that, and no condition on P, so it doesn't have to be abelian or anything, just a P group. And then there exists a subgroup, a P prime subgroup, E of the automorphism group of P. So P is a finite group, has a group of automorphisms. Then there will be some P prime subgroup E of the automorphisms of P, such that the Brouwer correspondent, so the local block, is just Morita equivalent to the algebra Okay, let's forget about this alpha for 1 second. Okay, so this is saying this is just the group algebra of P. So you take your P group, no getting away from that. You have to decorate it with a P prime group of the subgroup of the automorphism group of P. So if you have P, you have the automorphism group. Okay, and they form the group algebra of it. Okay, it's not quite as good as that. There's this interesting alpha. This alpha means, I'm not going to explain it, but this is just a twisted group algebra. Okay, so if you have any group, you can, and you have a element in the second cohomology group of that group with coefficients in the invertible elements of your ring of coefficients, then you can form a twisted group algebra, which has a basis made up of group elements. The multiplication is just twisted by this by a co-cycle corresponding to this class. Okay. Okay, for some alpha. Right, but so I mean, it's telling you that these Brouwer correspondents, well, there are very few of them, right? So for a fixed P group P, how many choices? Okay, there's the automorphism group. We could find several whichever subgroup you want, and then P, which is E, and then there's this another small group, or not, well, second cohomology group, and then you form your twisted group algebras, and that class is going to cover all Brouwer correspondence, okay, with the given Diffie group. So what this is, if you combine, if you throw in the structure theorem of Kuhlshammer with the abelian Diffie group conjecture, it's really saying that the abelian Diffie group conjecture sort of confirms what I was trying to say in my first lecture, confirms sort of at the level of the derived category at least, this philosophy that there are very few blocks, okay, of the maxim that there are very few blocks, okay. So that's, at least for me, one of the reasons why this conjecture is so interesting. Actually, I knew when I said small, I knew I was going to make somebody object. What I meant was finitely many possibilities. I mean, it's fixed, right? Okay, no. So it's prescriptive. The theorem of Kuhlshammer is prescriptive. The alpha and the E is coming from the local structure.
Alpha
okay.
From Schur's lemma.
So alpha is coming from the fact that if you have a group acting on a group of matrices, therefore by inner automorphism, and you try to make it inner, a homomorphism, you're going to get projective representations. Yeah. So it's the same alpha. It's coming from the same, yeah. And this E is, I mean, if you starting with your group G, this E is something that is in the local structure. It's part of the local structure of the block B, which I have not defined. Okay, and so is alpha. It's all popping out. Okay, so that's one. So that's a little blurb on the abelian Diffie group conjecture. Then, still keeping with the condition, why abelian? Well, there's another conjecture, even older than the Brouwer abelian Diffie group conjecture, which has generated a lot of work, I guess, in the last 10, 15 years. And this is Brouwer's height zero character conjecture. So let me state that. And this is not really a structure theory, structural conjecture. It's a characterization of being abelian. Okay, and it simply says that P is abelian if and only if the following arithmetic condition holds. Namely, that so we've seen in Gabriel's talk, the P part of a character degree is really important, and P being abelian is conjecturally equivalent to the fact that if you go across all characters of your block, then at least the P part of their degree is the same. And I should say here that one direction is now is known. Okay, the theorem. It's sort of, like I said, it's a theorem which goes through the classification of finite simple groups. So first we needed a reduction theorem, and then we needed to be able to check, so which required waiting for many years before we got enough information about the block theory of finite simple groups to be able to do every case. And so the final cases was settled by myself and Gunther Malle around 2012. So this direction is done, and in the reverse direction also there's a lot of progress. Okay, so this one is a weird statement, okay? And I think nobody has ever, to whom I've ever spoken, has any idea how Brouwer made this conjecture, because he did not have many examples, I think, he worked out. But anyway, it seems to be true, or at least, well, one direction hopefully is true. And okay, but this brings me to a very interesting question. So, okay, this is a characterization of the defect group being abelian. Okay, it's a theoretic characterization. Okay, but this conjecture, then, if it were true, would very easily give you the answer to the question: if B and B prime are Morita equivalent, I should say here over O, then, and if P has abelian defect, so B has, if P, yeah, I mean, right, B has abelian defect groups, then B prime has abelian defect groups. So namely, Morita equivalence preserves being abelian. Okay, and if you have the height zero conjecture, yes, because if two blocks are Morita equivalent, then you can show that there's a bijection between their characters. That's easy, but it's a height preserving bijection, so it will preserve the P part of these things. I mean, it'll preserve this condition, and then you'll get it. Okay, but this question, this is a much weaker question than Brouwer's height zero conjecture. Okay, because not asking for a direct characterization of being abelian. It's just saying that if two guys have the same module categories, their defect groups are abelian. But this is open, so we don't know how to prove this. Okay, and so I think there should be some homological way to get at this question. But right now, okay. But that brings me to a more general question. So if you find this one too easy, then you can try just a more general question, which is that does Morita equivalence preserve the isomorphism type of the defect group? So if B and B prime are Morita equivalent block algebras, we know that they have to have the same defect, so their defect groups have to have the same size, that we know. Do they, so are they actually isomorphic? This is wide open, because of course if we could answer this question in the affirmative, then we would have an answer to this question. And let me put here it really matters how you can phrase the question over little k or over O. Okay, so if you phrase it over little k, it becomes a much, much harder question than if you phrase it over O. And the reason why, if you think about this a little bit, if all you're asking is that there's a Morita equivalence between the block algebras over the field of characteristic P, this is satisfied, for example, if you take two finite P groups, okay, take their group algebras over field of characteristic P, then there will be only one block, and being Morita equivalent, both of them are indecomposable. Being Morita equivalent just means that the Kp is isomorphic to Kp prime. And so if you want the defect groups to be isomorphic, you will come to this very old, hard problem. Namely, if you have two finite P groups whose group algebras over field of characteristic P are isomorphic, are the groups isomorphic? Okay, so the modular group algebra isomorphism problem, that is very hard, and I don't know, the experts, people who've thought about it are sort of not very convinced that it's going to be not very confident, let me say, that it'll have an affirmative answer. So maybe for starters, you want to make life a little bit easier for yourself and give yourself the stronger condition that you start with a Morita equivalence over O. Okay, at least on the face of it, stronger condition. Okay, and then try to.
Is there evidence for this question?
Which question?
The general question.
That's a very good question about evidence, because, I mean, we don't ever look for a Morita equivalence between two blocks which don't have the same defect groups. We never try to compare blocks if they have, because we are always focused on, proving, sort of starting from the local side and then getting some group. So I think I would be pretty shocked if over O this was not the case. It would, well, yeah, it would. I'm not sure. I mean, I'm just hanging on that hope, it should be correct, this thing. Actually, it will be very exciting if it's not correct. Okay. Yeah. So I'm not scared. I just don't know anything. But I guess at this stage, if I had to bet money on it, I would say yes. It's going to have an affirmative answer. Because I mean, lots of invariants we can calculate. Okay, so I better move on. Final thing. Okay, so I was talking about general blocks. Then I said, okay, I like abelian defect group, so spoke about that. Now I'm going to specialize even further. I'm going to specialize the prime. Here, so it's still abelian defect, but now only the smallest prime. Defect and p equals 2. Okay, and now this is really where, this section is there to really illustrate that, the group theory is very important for the block theory. Okay, so why is abelian and p equals 2 sort of a significant situation? Well, I want to put down a theorem, classic theorem of John Walter from 1969. So it says a bit more than this, but I will just say it for. Let G be a finite simple group. If G has abelian seal of two subgroups, then G is isomorphic to one of the following simple groups. So the two-dimensional special linear group at the prime 2. Well, you want it to be simple, so let's make it n greater than or equal to 3. The projective special linear group of dimension 2 at some odd primes q, where q is greater than or equal to 5, and q is congruent to 3 or 5 mod 8. Some regroups of type G2, or 2G2. Q should be greater than or equal to 27, and an odd power of 3, and as is totally par for the course for finite group theory, one sporadic simple group, J1. Okay, and I should say, I've written it like that. In the original paper of John Walter, 110 pages, he doesn't quite identify the regroup. So in this slot, he gives some conditions on the group, but the fact that they were actually these regroups took actually quite a long time. I think it was only finally settled in 1980 that these are the groups that only groups that satisfy Walter's condition. I'm sorry, finite, simple, non-abelian. Non-abelian. Right, excuse me. No. Wait, no. Sorry, what did you say?
It could also be cyclic.
The CO2 is trivial.
Oh, right.
So
No. Finite, simple, okay, the group is, I can make it non-abelian, then you're okay? Yeah, finite, non-abelian, thank you. Thank you very much for that one. Non-abelian, yes. Yes, thank you. Okay, so, now one way to think about this is that there are very few finite simple groups, and therefore very few actually finite groups. From here you can deduce that, whose CEEL of two subgroups are abelian. Okay, so you might say then, okay, maybe one should concentrate on two blocks with abelian defect, because right, if there's so few groups around, you should be able to do something with the blocks. Okay, first just one remark, and you can, but this analogy between groups and blocks doesn't go over like bang on the nose. So you have many situations of blocks of two blocks of finite simple groups which have abelian defect groups. Let me just give you a cheap example. Okay, so example, if n is a triangular number, then any alternating group of the form of degree an plus 2 has a block at least one block with defect group isomorphic to C2 cross C2. Okay, so in some ways there are loads of instances of blocks of finite simple groups with abelian defect, but in fact there is a theorem about the structure, about how these possible blocks arise. And again, this theorem is reliant totally on the knowledge of finite simple groups. So, and this is work of Charles Eaton and myself, but Kulshammer and Benjamin Sambale, who's in the audience, from I think it came up 4 or 5 years ago, and it says, okay, so let G be a finite. I'm just going to weaken simple to quasi-simple. It's not so important for this talk, but for block theory it is an important weakening. Quasi-simple finite group, and B, do I need to say non-abelian? I'm just going to say it because I don't know what, non-abelian group, and let B be a block of G, 2 block now, be a 2 block of G with if B has abelian defect groups, then one, actually it's not mutually exclusive or more, it can happen, of the following hold. Okay, the first thing is that, of course, we have these groups of John Walter himself. Okay, so G could be one of Walter's groups. I should say G mod Z of G. So we go to the simple. One of Walter's groups. And this will always happen if B is the principal block, and it turns out it only happens when B is the principal block. So we're going to get this situation regardless, okay? And then what else? So then again, group theory, there's one sporadic case, which is an outlier. So it's G is the Conway 3, and B is non-principal block. And the defect group is elementary abelian of. Oh, I'm almost going. Yes, but for once I'm more or less on time, so I will finish. Okay, so you get this new guy here. You get lots more blocks, but all the new ones you get are sort of have a easy structure. So B is Morita equivalent to its Brouwer correspondent. That can happen. Okay. And lastly, okay, B is Morita equivalent. Let me write it like this. P is a direct product of a group Q with C2 cross C2. And B is Morita equivalent to one of two algebras. A KQ tensored with the group algebra of the alternating group on 4 letters, or KQ tensored with the principal block of the alternating group on 5 letters. Okay, and that's it. So it's somehow everything that we're getting beyond Walter's theorem is these very, so remember, if B is Morita equivalent to B star, that is Morita equivalent to the semi-direct product. And that's, I mean, if we can get to that stage, we are really happy. And so, yeah, okay, so so you have this thing, and of course from it and doing a bit more work, you can derive many finiteness results. Okay, so Donovan's conjecture, let me just write one. Consequence, for example, that comes out. There's more, but Donovan's conjecture holds. For all 2 blocks, not just for simple groups, but any group with elementary abelian defect groups, and so on. You can get situations where you can also say, okay, Brouwer's conjecture holds, and so on. Okay, so I think this is a good time for me to stop.
Questions?
Does your proof of this theorem use Walter's theorem?
I mean, it uses much more, uses the classification. Yeah, right. And it uses, yeah, lots of, I should say, for nailing down this. So it uses a lot of block theory, but for nailing down this case, it's using Erdmann's structure theory for blocks with Klein 4 defect, for example. And I mean, we throw everything possible that we have at our disposal for blocks of finite groups of Lie type to get it. I mean, it's just a lot of hard work. Yeah.